Hello, you can see for yourself what the title of the video is, and the first question that may occur to you is why would you ever want to look back in time anyway? Because simulation starts at time 0 and then time advances, an increasing positive number of the number of nanoseconds that have passed. Why do we want to do this in simulations? It may seem obvious in formal why we would wish to do this, because formal doesn't need to obey the what's called linear temporal logic kind of semantics necessarily, but in simulation it seems a bit counterintuitive. Why? So as you may guess from its name, $past is a function that looks back in time, and what it does, it returns the value of some expression at a previous number of cycles ago. So in SVA, everything is evaluated on cycles that we define with some kind of clocking expression, like at neg-edge clock, for example, as shown down here. And what this does is return the value of a n number of cycles ago. So n defaults to 1. $past actually has 4 different parameters, and only the first one is mandatory. The rest are optional. So if we don't provide a second parameter, it defaults to 1. So how we can use this is shown here. So if en is true, this implies that at the same cycle op equals the value returned by this call to the $past function, and it's the value of IP 2 cycles ago. So at this cycle here, cycle 2, the value of IP 2 cycles ago was 0, so therefore op does equal the value of IP 2 cycles ago. And likewise at cycle 5, the value of IP 2 cycles ago, 1, 2, was 3, therefore we have another pass. Now if you're using formal, it's best not to make n a big number. So by big we mean almost anything above 1, because it means the tool has to remember the previous n possible values, not specific values, n possible values, and it rapidly explodes the state space. So you're probably best avoiding using the $past function at all in formal. As well as $past, there are other things that can look back in time, like $stable, $rose, and $fell. All of those three I've just mentioned provide a history of 2 cycles, the current one and the previous one, so they are looking back in time as well. Another example here is using the triggered function. So every sequence has a built-in function called .triggered, and it is true whenever the sequence finishes. So here we've got a definition of a sequence called RST that defines a sequence, and RST.triggered represents any cycle in which that sequence has just completed. So we're using that in this property here. So we're saying if we have A followed by RST.triggered, meaning that sequence here had just finished, followed by B, this implies that C should be true on the next cycle. So let's look at these waveforms up here. We've got A being true there. On the next cycle, RST triggered here is true. And it's true because we've had reset followed by not reset 2 times, followed by reset. So that sequence ends here. Followed by B implies C is true the next cycle. So the property, which started being evaluated here, 3, actually completed at cycle 6. However, what we will notice here is that in order for it to have passed, i.e. reset triggered occurred at cycle 4, we needed to have been looking at what reset was doing all the way back at cycle 1. So we're actually going further back than the property was active in effect. So RST.triggered is always being evaluated regardless of whether we've observed A yet or not. What this slide also shows is another property here in which the RST.triggered has been replaced by RST. So this is just to demonstrate that saying a sequence .triggered is not the same as saying the sequence. Okay, this represents a boolean, RST.triggered represents a boolean, and RST represents a sequence. So they're not the same thing. So the reason we use these kinds of functions that we've seen already, like $past and RST.triggered, is because often problems are easier to express in the terms of, rather than cause and effect, which is the normal way, if something happens then something else must happen in the future, that's cause and effect. Some event occurring must cause an effect in a future cycle. It's often easier for some kinds of problems to say if a specific event occurred, then what must have gone before that event occurring should have been this sequence of things. So it's not cause and effect, it's saying any event must have had a prior cause. So it's the opposite way of looking at things. Some problems are easier to describe in that way, which is why it exists. Now we've seen already using $past, and we said that in formal this is not too good if you start putting numbers here, a big number. And so if you're trying to recover the value of mem read from 100 cycles ago, for example, that's a huge explosion in the state space, because the formal tool would have to remember the previous 100 possible values. So you're multiplying that 100 entries by all the possible values they could have been. So it's a huge increase in state space for no really good reason, because what we can do instead is use auxiliary code. So if you're interested in how this auxiliary code works, if you search on the Cadence support site for a webinar called Formal Optimization, then you'll see this described, and it's also in the Jasper Gold online fundamentals course as well. So auxiliary code is just helper code. It only exists to help us write properties or make things more efficient for a formal tool. So what we've got here in this code and what it looks like is exactly like RTL code. So this kind of code would be in some kind of assertion module or checker. It would not be inserted in the same file as your RTL code that you're trying to verify. And all this auxiliary code often looks like is just setting flags, clearing flags, or counting the number of occurrences of something. So here our requirement is an acknowledge must only occur after a request that has not been acknowledged until now. So we describe a flag, rec without ACK. And if reset occurs, we clear the flag. If we have a rec and not an ACK, then we set the flag. And if we actually have an ACK, then we clear the flag. So all we're doing is setting a flag under certain conditions, clearing it under different conditions. And in order to implement now this requirement, what we do is have a simple assertion. A implies same cycle B. So if we have an ACK occurring, it must mean we've had a previous request. Okay, and we know that because we stored it on the value of an RTL signal. Okay, so unlike assertions, which can be overlapping, auxiliary code can never be overlapping. There's only one instance of it, so it reduces the state space significantly for formal problems. Okay, so that concludes the presentation. Hope you found it useful, and thanks for listening. Goodbye.